Hello, my name is Yong Chung, and in this study, we investigated what the role of object file is in visual working memory, and that it can facilitate integration of changing features. A lot of visual working memory studies often primarily use static and stationary stimuli, but when you encounter an object in real life, of course, we actually see it in many different states. Just like the moving toy car in the video, objects' features dynamically change around due to different angles, lightings, viewpoints, and etc. Previous works on dynamically changing stimuli have shown that people are able to temporarily integrate the changing information together. However, other works also show that people's memory lags behind the current state when tracking changing features of multiple objects, and that this lag gets larger with larger set size. Our question is, how will motion of stimuli affect the memory of dynamically changing stimuli? And this is especially intriguing because motion often induces features of objects to dynamically change around, while static objects do not change much. But when you suspect something is part of an object or when you generate an object file, even if the features are changing around, we try to integrate all those information into one single object representation. So will motion induce integration and averaging of the features, and how will that affect the lag in memory? We can test this out using much simpler stimuli such as color dots. In our experiment, two dots were presented on the left and right sides of the screen, and they changed the color smoothly. There were two main conditions: stationary condition where the dots did not move at all, and the moving condition where the dots moved along the preset path. At the end of the trial, we asked participants to report the last color they've seen. This is our experimental design. Again, there are two conditions, moving and stationary, and we also vary the set size as well. Here's our prediction. When the dot is stationary and changing its features, this is somewhat unnatural in the real world, and people will perceive it as just color changing, like painting it over and over again. This will not result in integration, but just simply updating the colors. And when asked to report the last color, people will report the actual last color that they thought they saw. However, when the dot is moving around and changing its features, this is a lot more common in the world, so people will perceive the dot as one object that is continuously changing its color. This will induce temporal integration of the colors, such as averaging of the colors, just like how you do with real object. This will cause the representation to be seemed more lagged because people are incorporating more past colors, but more precise because people are averaging over many noisy color representations. For the results, we looked at the color errors and used non-parametric circular statistics as indices of two main components, lag and precision. Lag is the distribution mean shift from the 0-degree line, and negative shift indicates more lag or that participants reported more towards a past color. Precision is how wide the distribution is, and higher standard deviation indicates worse precision. If feature integration happens in moving conditions, we expect the lag to be larger and precision to be higher or better in the moving condition. We can look at the data using the bar graphs. First, we can look at the lag or the mean shift. If you look at the stationary condition, there are actually somewhat of positive shifts. However, the effect size seems to be really small, and they don't change much with set size. For the moving condition, there were indeed negative shift, indicating that there were more lag, or participants reported more towards the past color when the dots were moving around, and this lag seems to be larger with set size 2. When you compare the stationary versus moving, there is indeed more negative shift or more lag in the moving condition. The same trend follows in the set size 2. We can also look at the precision data. In both stationary and moving condition, the precision seems to get worse, or the standard deviation is higher in the higher set size, which aligns with all the other working memory studies. However, interestingly, when you compare the stationary versus the moving condition, the precision seems to be better, or standard deviation is lower in the moving condition than the stationary condition. The same exact trend follows in set size 2 as well. In summary, we found an increased lag in color memory representation when participants are tracking moving dots, and also increased precision when dots are moving around. So going back to our prediction, these two patterns of results aligns with our prediction of integration and temporal averaging when moving. Due to incorporation of past colors, representations seem to be more lagged, but also due to averaging of multiple noisy color representations, reports are more precise. And it's really the combination of both lag and precision effects in the moving condition that yields results that can be together explained by the feature integration. Now, because a moving condition and stationary condition are very different, it is possible that some sort of lower level differences between moving and stationary stimuli also contribute to the results. To test this, we plan to compare two motion conditions, one designed to induce continuous object perception and one designed to break the object file. Previous demonstrations have shown how to utilize different motion manipulations to break continuous object perception, and one of them is this implosion manipulation. In the continuous condition, stimuli move behind the occluder smoothly, as if it would in real life. However, in the breaking condition, the stimulus disappears as it hits the occluder and pops out on the other side of the occluder, possibly breaking the object file and breaking the feature integration. Thank you very much for your attention, and thanks to everyone in the lab who has helped me through this project.